Hello and welcome. Today, we're going to shed a little light on, well, light itself. We're going to dive into the fundamental rules that literally govern how you see everything, so let's jump right in.
Really stopped and thought about it? How does the world out there get inside your head? How does the image of a tree or a book, or even the screen you're looking at right now, actually register in your brain?
It really is that simple. It all comes down to light. You know this instinctively. If you're in a pitch-black room, the world just vanishes. Light is the absolute, non-negotiable ingredient for vision.
Okay, so for us to see anything, we obviously need a source of light. But that brings up a pretty big question, right? Where does light come from? And more importantly, how does it let us see things that don't make their own light?
So here's the scientific breakdown. Light isn't a thing. You can't hold it. It's pure energy. It's a special kind of energy that travels from a source, bounces off an object, flies into our eyes, and our brain performs this incredible magic trick of turning that energy signal into a picture. It's pretty profound when you think about it.
And this is a really crucial distinction to make. We see millions of things all day long, but an absolutely tiny fraction of them are actually producing the light. Most objects are just light borrowers.
And here is the perfect example, right up in the sky. The sun is what we call a luminous body. It's its own powerhouse, a giant fusion reactor pumping out insane amounts of light. The moon, on the other hand, is non-luminous. It's basically just a giant dusty rock. The only reason it shines so brightly in our sky is because it's acting like a massive celestial mirror, reflecting the sun's light back at us. And this brings that huge cosmic idea right back down to your room. The book on your table isn't glowing by itself, right? It's non-luminous. You can only see it because light from a luminous source, a lamp or the sun through a window, is hitting the pages, bouncing off, and traveling into your eyes. It's the exact same principle.
All right, so now that we've got that down, let's move on to the single most important rule that light follows. It's a rule that explains so much about our world. And you know what? It's surprisingly simple.
That's it. That's the rule. Light travels in a straight line. Now, scientists love to give it a fancy name, rectilinear propagation, but it all boils down to that one simple fact. And this principle explains everything from how shadows are formed to how a basic camera works.
And the proof is something you could do right now. If you look at a candle flame through a straight straw, you can see it perfectly because the path is clear. But if you bend that straw just a little bit, poof, the flame is gone. Why? Because you've blocked that straight line path the light was taking to get to your eye.
And this isn't just a suggestion, it's a fundamental law of physics. As long as light is moving through the same medium, like air, it is going to travel straight. And that predictability is what allows our visual world to make any sense at all.
And if you want to see this rule in action, look no further than a simple pinhole camera. Light rays from the top of the candle travel in a straight line down through that tiny pinhole to the back of the box. And rays from the bottom of the flame travel straight up to the top of the box. The result? A perfectly flipped, upside-down image. It is undeniable proof that light does not curve.
Okay, so this is where it gets interesting. If light always travels in a straight line, what happens when something solid gets in its way? Well, that's when you get the art of casting shadows.
You see, a shadow is nothing more than an area where light is being blocked. Because light can't just bend around that opaque object, it leaves a dark region behind it. Every single shadow you've ever seen is a direct consequence of light traveling in a straight line. But not all shadows are created equal. It really depends on the light source. If you have a tiny focus point of light, the shadow it casts is going to be super sharp and uniformly dark. This region of total shadow has a specific name. It's called the umbra. But what happens if our light source is bigger, like a frosted light bulb or a big candle flame? Well, the shadow gets more complex. It's no longer just a simple dark blob. You'll see a dark center, sure, but you also get this fuzzier, not quite so dark region around the edges. This is where we get two distinct parts. The umbra is still that central, completely dark area where all the light is blocked. But that fuzzy, partially lit outer edge, that's called the penumbra. That's the area where light from some parts of the big source is blocked, but not all of it. And that's why the edges of most shadows you see every day aren't perfectly sharp. So for our final section, let's take everything we've just learned about light and shadows and rectilinear propagation and scale it up. I mean, way, way up. And here's the amazing connection. The exact same physics that creates that fuzzy shadow from a lamp in your room is what creates a solar eclipse. Eclipses are just shadows. They're just shadows on a cosmic scale.
And this is what it looks like. During a solar eclipse, the moon, which is just a huge opaque object, passes in front of the sun, our extended light source. And as it does, it casts this absolutely massive shadow that literally races across the face of the Earth.
And here, we can map all our terms right onto this incredible event. The sun is the source, the moon is the object, and the Earth is the screen. If you're lucky enough to stand in that narrow path of totality, you are standing in the moon's umbra. If you're in the much wider area around it seeing only part of the sun blocked, you're in the penumbra. It's a perfect, cosmic-sized demonstration of everything we've just talked about.
So, we've firmly established that light's straight-line path explains so much, from pinhole cameras to solar eclipses. But what if I told you that under some really extreme conditions out there in the universe, that very rule can be broken? That light itself can actually be bent? Well, that is a story for another time. Thanks for watching.